Hello students, so welcome to this lecture on inverter, which is kind of approximated to an RC circuit, and where R represents the switching resistance of the transistor which is operating at this particular, at any point of time, and C represents the capacitance seen at any of the output nodes or any kind of a diffusion nodes, which is of interest to us. So what we will see is we'll take an inverter circuit and then try to approximate the RNC, an approximated RC circuit, and proceed further. Okay, so moving on. So what we had seen is, an NMOS transistor, a unit NMOS transistor has a unit resistance of R. So this is the R, and if I scale the transistor by k times, then the switching resistance is going to scale down or is going to decrease by k times. So that's thereby the switching resistance is of the value R by k. Right, so the width, if the width of the NMOS transistor is k times the unit NMOS transistor width, the unit NMOS transistor width is anyways 100 nanometers, which we had seen previously. So if it is k times more than that of the 100 nanometers, the capacitance will be k times into C, where C represents the C represents the capacitance for a unit NMOS transistor. Right, and similarly, k times the width of the NMOS transistor will give me the switching resistance of R by k. Right, so to replicate that into a transistor level, so this is what we have drawn. So at the gate side, the capacitances will be scaled by k times. Diffusion and then the parasitic capacitances will be scaled by k times, and the switching resistance is denoted by R by k. And for a PMOS, a unit PMOS is again a width of 100 nanometers. That is the unit PMOS. So I'm talking about the unit PMOS. All right. So in this case, the switching resistance of a PMOS will be nothing but twice that of the switching resistance of an NMOS. Again, it is attributed to the lower mobility which the holes have with respect to that of the electrons. So we will have two times R, where R represents the unit NMOS switching resistance, and if the PMOS transistor is scaled k times the 100 nanometer, which is the unit PMOS transistor's width, so then in that case we will get 2R by k. So the overall switching resistance of the PMOS transistor will be scaled down by k times. The capacitance, however, will be scaled up by k times. So k into C is what we will see for the gate capacitances and as well as for the depletion and then the parasitic capacitance. So that is what is represented for the PMOS structure here. The PMOS structure, the gate side, you will see a K multiplied by C capacitances. Note that it is connected to the VDD. The gate side is at a higher, the body is at a higher potential than that of the gate, so the body is actually connected to the gate, and the body is connected to the VDD terminal. So that's what I have written here. And you can see that the capacitances are scaled up by k times, kc, kc, and kc. The switching resistance is anyways 2R by k. So this is what is denoted here. So the difference here on the PMOS side as well as on the NMOS side is the switching resistance is the difference. The capacitances, the gate capacitances as well as the parasitic and the depletion capacitances remains the same. Right, hope you have understood this. Moving further. So just to summarize this, the unit NMOS, so this is the unit NMOS we have. And I'm saying this as a unit NMOS because the moment I see W, W is equal to the width of the NMOS transistor as for lambda, where lambda is equal to 25 nanometers. 2 lambda will be the channel length of the 65 nanometer technology node, which gives us 50 nanometer of the channel length. So 4 lambda will be 100 nanometers. So that is our unit NMOS, which we write it as 1. A transistor, an NMOS transistor with the numbering of 1, with the labeling of 1 represents that it's a unit NMOS. Similarly, for the PMOS transistor, width of 4 lambda, length of 2 lambda, and then denoted by a 1 here on the transistor side is nothing but a unit PMOS. If I have a width of 8 lambda for the PMOS, if I have a width of 8 lambda, that means I'm writing a 2 here, which means that the width is twice that of the unit PMOS transistor. This is a PMOS transistor, so 2 represents twice the width of the unit PMOS transistors. Then we can say that it is not a unit PMOS. It is twice the width is 2 times that of the width of the unit PMOS transistor. So this is the general the naming conventions of the transistors. So this particular portion. So what we have seen is actually the channel length. So the channel length in all these cases remains 2 lambda. So we generally don't change or modify the channel length. What we change is the W parameters, right? And then those W parameters can be represented in terms of the scalar quantity here. Instead of k times, I've written 2 times, or I can write it as 4 times, or I can write it as 10 times. What it represents is the width is scaled 2 times or 4 times or 10 times more than that of the unit PMOS or NMOS transistors. Alright, so in most of our digital design, the channel length doesn't change. So we are not going to manipulate the channel length. We are not going to scale the channel length. The channel length, we are going to limit it to the lowest possible channel length, which will be 50 nanometers or 2 lambda for a 65 nanometer technology node. Right? What we are going to change and what we are going to represent, the scaling is nothing but for the width dimensions. Hope this is clear. Moving ahead. So we have designed a unit inverter. So it's an inverter, but it's a unit inverter, and what it represents is the unit inverter is the lowest transistors, the lowest PMOS dimensioned transistors, the lowest NMOS transistor dimension, and where the current of the PMOS and then the current of the NMOS are equal. So that's what a very brief definition is. What it really means is, can I have an inverter with the lowest possible sizes of the transistors of PMOS and NMOS with the equal rising resistance and then the equal falling resistance, right? So if I want the equal rising and falling resistance, so what it means is if I have a step input here at the input side, right, and if it is step input, I know that the NMOS transistors will be on, so NMOS will be on in that case, PMOS will be off. Okay, so all my switching resistance or whatever, when we do the delay calculation, it is only through the NMOS current. The discharging of the capacitor takes place through the NMOS transistors current. So I will actually utilize the NMOS current, IDS current, and then calculate the propagation delay. Similarly, we had seen that the switching resistance, which we calculate using the NMOS transistor, because that is the one which is operating and that is the one which is discharging the capacitor and bringing the output node voltage to 0. So that will give me the fall resistance. Alright, whatever is the current of the NMOS, that will help me in establishing the fall resistance of the NMOS transistor. Similarly, if I have this step input going back to 0, in this particular transition, I will know that the PMOS transistor will be on and the NMOS transistor will be off, and in that case, I will get the rising resistance because my output node is rising to a VDD value. Right, so the rising resistance, I can get it from the PMOS. So what we need is, for defining or designing the unit inverter, is the PMOS transistor should have an equal, the PMOS transistor should have a rising resistance, or the switching resistance of the PMOS transistor should match with that of the NMOS transistor switching resistance. And in the long channel model, we know that the resistances will match if the current matches. The maximum current, the saturation current and the linear current of the PMOS should match with that of the saturation and linear current of the NMOS. And in that case, we should be able to get the same resistances, right? And that is possible only if if I take the beta of the PMOS to be equal to the beta of the NMOS, right? Which means that the width of the PMOS should be equal to twice that of the width of the NMOS, right? And what we still have the design requirement of the unit inverter is it still should be of the lowest size. So the lowest possible size on the NMOS side I can get is W is equal to 4 lambda. That is the lowest possible dimensions I can get for the NMOS. So for the PMOS, so I will have the width which I need to have to be twice that of the width of the NMOS. So that becomes 8 lambda. So the unit inverter is not made up of unit PMOS and unit NMOS, right? It is actually made up of unit NMOS, but the PMOS side, it is twice that of the unit PMOS. So the width here should be nothing but 8 lambda here for the PMOS, whereas the width of the NMOS is 4 lambda. And the reason for the unit inverter is we want the equal rise and the falling resistances. Right, so that is something you should make a note of it. Unit inverter is not made up of unit PMOS and unit NMOS. It is actually on the PMOS side, it is twice the width that of the unit PMOS, and on the NMOS side, it is the unit NMOS. All right, hope you have understood this. Moving ahead. So what we have now is a unit inverter which can be represented as 2:1. 2:1 represents the width of the PMOS side is scaled 2 times than that of the unit PMOS, and 1 represents the scaling is only 1 of that of the unit NMOS. So I have now 2:1, which will give me the equal rising and falling resistance. So what it really means is I will get equal amount of current on the PMOS and in the NMOS. Both the linear and saturation currents are of the same level. Now, if this particular unit inverter is actually driving one more unit inverter, right? One more unit inverter, that means 2:1, one more. So this output X node is connected to another inverter of 2:1, and then the output is taken. So I have an input provided to the first stage. So this is the first stage, and this one is our second stage. All right, so the input is provided to the first stage. I'm taking the output is cascaded or fed to the next stage, and then we will get the output. And both the inverters are 2:1 inverters, right? So in this case, how do I find out the propagation delay falling or whatever the rising? It of course depends on the output whether it is falling or rising. And if the input is rising, I will naturally get the output to be rising because it is 2 inverter stage. And if the input is falling, I'll naturally get the output to be falling. Right. So at this particular point, when I have 2 stages cascaded, it will be interesting to note what should be the overall capacitance here. Right. We should be able to establish that because we know there will be a capacitance, the parasitic capacitance coming from here. Right. And then there will be a parasitic capacitance coming from here, from this particular transistors to the body, and parasitic capacitance coming from the PMOS transistors terminal to the body. And then we have the capacitances on the gate side of the next stage contributing to the X node, and then the capacitance on the the gate side of the next stage NMOS transistor contributing to the X node. So once I have this capacitances, then I should be able to estimate what should be the switching resistance of this PMOS transistor, and then what should be the switching resistance of the NMOS transistor. And we know that the falling and then the rising resistances, that is the switching resistances, for a 2:1 unit inverter is nothing but same. Right? So if the switching resistance of an NMOS, we know that in a long channel model it will be around 560 ohms. So for a the width of 2 times the unit PMOS, the PMOS transistor will also have the switching resistance as that of the 560 ohms. Right? So with this particular parameters, so let's try to establish what should be the propagation delay. In this particular diagram, although it looks very, very dense, it is nothing but what I have drawn in the previous slide. So I've just drawn the capacitances here. The capacitances are nothing but 2 into C, because it is the scaling of 2 is there here on the PMOS side. The scaling of 2 is there, 2 into C, and then 2 into C here. On the NMOS side, for the first stage inverter, on the NMOS side, I have a scaling of 1. That's why the capacitances remains 1C, 1C, and then 1C. Right? The switching resistance for this, should be R, and then whatever is the scaling factor, it will be 1. The switching resistance of this for the PMOS, we know that it is nothing but 2R divided by K, which is nothing but 2. So I will get same as that of R. Okay, hope this is clear. This is being cascaded to the another 2:1 inverter. So I will get the scaling of 2 into the capacitance, unit PMOS capacitances. 2C here, 2C here. Again, the scaling is 1 here. That means I'll get 1C, 1C. And on the gate side, I'll get 1C. So the overall capacitances that I can see on the X node, the overall capacitances that I can see will be nothing but this particular capacitance in parallel with this particular capacitance. Of course, in the AC analysis or in the transient analysis, this VDD, we will consider it to be grounded. So this will be 1C plus 2C coming from the next stage inverter, and then 1C also coming from the next stage NMOS gate capacitance. So I will have 2C plus 1C plus 2C plus 1C. It will be equivalent to 6C capacitance that is being seen at the output node X. Right? Of course, it is not the output node X, it's an intermediate node X. Right? The output is still this, after the second stage. So I'm talking about this particular output node, which is an X node. Right? So which is nothing but the output after the first stage. Moving ahead. So I've just drawn here, this slide is very, very similar to the previous slide, just that the switching resistance I have drawn, which is nothing but R, and R here, and R here, and R here. Okay, hope this is clear. And of course, X will have a capacitance of 6 times C. Moving ahead, this is something we are anyways aware about it. This particular capacitances, the 2C capacitances here and the 2C capacitances here, which is having on both the terminals, it is a VDD, and then similarly the 1C capacitances here and 1C capacitances here, on both the terminals it is the ground. So any changes in the input side or any changes in the X output node will not have any change in the 1C and 2C capacitances here, the voltage across the 1C and 2C capacitances, because on both the sides it has a fixed potential of VDD or ground. And similarly, it will have the same effect on 2C and 1C on the second stage inverter. So any change in the input X node, any change in the output here will not have any effect on the 2C and 1C capacitances, because again it is fixed to the both the 1C and 2C capacitances are fixed to the DC voltage sources, the constant voltage sources. So it is also called as a non-switching capacitance. Alright, so that is what this slide says. Hope this is clear. Moving ahead. So this is what we have, 2:1 inverter, the switching resistance. So let me draw this. The switching resistance is nothing but R here. The switching resistance is nothing but R here. And the overall capacitance is 6C connected to the another next stage inverter, which is the output capacitance is 3C, because here it is nothing but 2:1. So I will get one capacitance, one 2C capacitance coming from here that we had seen in the last slide, and then one C capacitance coming from this particular drain to body of the NMOS. Right. So overall, on the output side, I will actually get 3C capacitance. On the intermediate output X node, I will get 6C capacitance. Right, so what should be the propagation delay falling from input to X node? Right, so I'm taking stage by stage. The first stage input and the first stage output is the X node. The second stage input is the X node, and the second stage output is nothing but the output node. Right, so the propagation delay falling and propagation delay rising is what I'm considering for the first stage. So from input to X, which is the output of the first stage, what should be the propagation delay falling, and similarly what should be the propagation delay rising for the input to the X node. So I've written the X node, and then X node sees a capacitance of 6C, And for the falling is anyways the NMOS transistor, which ensures that the X node discharges to 0. And for the rising, it is nothing but the PMOS transistor switching resistance, which makes sure that the X node is reached to the VDD level, and that's why the I have the PMOS transistor in wherever I want the rising propagation delay. I need the switching resistance of the PMOS transistor, right, which is connected to the VDD. Here the R switching NMOS resistance is connected to the ground. So the propagation delay falling will be nothing but whatever is the switching resistance multiplied by the capacitance of 6C. And of course, I can consider log of 2, or I can neglect it. So I will get 6 times R into C as the propagation delay falling. And similarly, the propagation delay rising will be nothing but 6 times into RC. Right? If it is a unit, if it's a step input, then I will consider the log of 2. Right? If it's a step input, I'll consider log of 2. If it is not given, that it's not a step input, then I can even neglect this log of 2. And I'll take the conservative approach of 6 times R into C. Right? Hope this is clear. The propagation delay rising and falling for the second stage, which has, at the output node, it has only 3C capacitance. So the propagation delay rising for the second stage is nothing but 3 into C multiplied by the R, the switching resistance. For the rising, it is the switching resistance of the PMOS, right? PMOS, it has a width of 2, so that's why its switching resistance will be R. And the propagation delay falling for the second stage, that is the input is X and then the output is output node, will be nothing but 3C into R. This R is nothing but of the NMOS, which is having a width of 1. C is the switching resistance of R. So the overall propagation delay falling for input to output, from input to output, right? And assuming that input is not a step input, it may be something else. So the step input is not mentioned here. So in that case, it will be nothing but the propagation delay rising plus the propagation delay falling. Propagation delay rising, if I have a falling, if I want to find out the propagation delay falling from the input to the output for the two-stage circuit, so this falling represents the output should be falling here. The output of the second stage should be falling. Right, so if I want to get the output of the second stage to be falling, that means I need to have a propagation delay falling here. And because the inverter, the second stage is an inverter, the input to the second stage should be a rising input. And that's why the first stage, I need to calculate what should be the propagation delay rising. Because the first stage output will be rising, then only the second stage inverter output will be falling. Right, hope this is clear. So I need to find out the propagation delay rising for the first stage and then the propagation delay falling for the second stage. So that's what I've written: input to X node of propagation delay rising plus the propagation delay falling for the the input to the output. So overall it will be nothing but, this is nothing but second stage will give me 3 RC, the first stage will give me 6 RC. So overall it is nothing but 9 RC value. Right, very conservative approach when the input characteristics is not given. When the input of the step input is not given.